Hello, I'm going to give you a quick overview of Chapter 6, kind of a lecture without being in class. Okay, so we're going to cover these topics: equilibrium, we talked a little bit about last time, and then how we use Newton's second law for an object that's accelerating or at a constant velocity. We'll talk about the nature of the friction force, and then some more examples of work on in class. Okay, so Newton's second law we looked at before. So it relates the net force on an object and an acceleration. So if you have more than one force acting on an object, like this box over here, right? So there's two people pulling at it. The tension is up at an angle here. The tension one is straight down. And if we added those, kind of did a tip to tail addition, we'd see that the net force was actually down and to the right. And so that's where the acceleration would be. So keep in mind that this is a vector equation, right? So these are, when we calculate the net force, we have to sum all the forces that are acting on the object, and they're vectors, right? So we need to take their directions into account. Once we get that sum, we can divide by the mass to get an acceleration. So a crucial step for this is to identify the forces on an object. And so in Chapter 5, we focus more on free body diagrams. So just remember that this is a picture that's going to represent all the forces acting on an object. So in this case, you have, I'm not really sure exactly what this is, ice, maybe a block of ice with a rocket on the top of it that's propelling it to the right. So there's thrust from the rocket that will make it move it to the right. There's a contact interaction between, let's say, the block and the ground, right? So there'd be a normal force acting on the block. And then we have a long-range interaction with the Earth that creates the force of gravity. So our free body diagram, we take that block and just represent it as a point, and actually our system is the block plus the rocket, right? And just looking at forces acting on that. So we have the thrust to the right, we have the normal that's upward, and the force of gravity that's down. And if we did the vector addition of these two are equal to each other, so the net force in the y direction is 0, and we end up with a net force in the x direction. Okay, so for an object to be in equilibrium, its acceleration is 0. And we talked about this when we did Newton's first law, right? So that means if the net force is 0, it could either be going at a constant velocity or it could have a velocity of 0. Okay, so when it's velocity of 0, that's static equilibrium. When we have a constant velocity, that's called dynamic equilibrium. But regardless of whether it has a constant velocity or 0 velocity, the net force is 0. Right, so that means the net force in the x direction is 0 and the net force in the y direction is 0 for an object in equilibrium. Okay, so as we do two-dimensional motion, one of the common problems that we'll work with is an object that's moving along an incline, like we've seen here. And so if you, again, look at the free body diagram for this, it has, even if it's sliding downward, there's going to be friction that will resist the motion. There's always a normal force, and again, that's going to be perpendicular to the surface. So the surface is this way, my normal force is there, and the force of gravity is just straight down. So the way that we almost always will set up our coordinate axes when we're doing these kinds of problems is to have the x coordinate along the plane and the y coordinate perpendicular to it. And okay. And so that's fine in terms of the friction is in the x direction, the normal's in the y, but the force of gravity is actually not in just x or y. It has components in both directions. So let me actually just draw this for you here. So it's very important that you know how to break gravity into its components on the incline. So let's draw this out again. So we have, and I can flip it over, it doesn't really matter, but so we have an inclined plane. Okay, so it's got some angle theta. And we have an object that's sitting on it, and if we just are isolating the force of gravity, I like to draw force of gravity going all the way down to the bottom of the incline. That kind of helps me with the geometry. Okay, so force of gravity is going to be perpendicular to the ground. And so I have one triangle here, right? I have, so let's draw this with an outline in red maybe. Okay. Maybe my pen works. Maybe we can. Okay, So this is 90 degrees, this is theta, and then here, this angle would be 90 minus theta. Okay. So let's call that maybe theta 2, or we could call it phi, give it a different Greek letter. Okay, so we'll call that phi. All right, and now let's just draw this again. Some kind of shape here. All right, so here's my object. And like I said, we're always going to have kind of our x-axis along the plane and the y-axis perpendicular to it. So gravity has a little component along the plane and then one perpendicular to it. Okay, so that's my x component of gravity and my y component. And here's Fg. And now here is my 90-degree inside the force of gravity. So if we look at this triangle, a little difficulty with my pens here tonight. It's not going to open. All right, we'll just sketch it in with a pencil. Right, so we have here, here, and here. Those are the three legs. Gravity is always the hypotenuse of that triangle. So if you look at this big triangle and this little triangle share the same angle, which I had called phi, which is 90 minus theta. So now if we look at the small triangle just in gravity, we have the 90 degrees, we have phi. I'll just draw that again by itself. So that's the part down the plane, that's the part into the plane. Fgx, Fgy, and Fg. So now this is phi, that's 90 degrees, and so that means in here, this is theta, right? So it's just like this big triangle, theta, phi, and 90. We have phi is the same angle for both triangles, right? So that makes this one 90. So now I can do my trick. I can say that the sine of theta is Fgx over Fg. So Fgx equals Fg sine theta. Okay, and then I can do, here's theta again. I'll do my cosine. Cosine theta is Fgy over Fg. So Fgy equals Fg cos theta. Okay, so crucial that you need to understand how to do that. And again, I think the key to that is just realizing that the two triangles, right, the component where we break gravity into its components and the big kind of wedge where you can make gravity one side, share that same angle. That's the easiest way to get to it. Okay, but you should be able to derive that yourself. Okay, so let's do an example. So we're going to use a strategy, and we'll actually give you these in class, or you can download them from Canvas. We have a dynamics worksheet, and it's a nice way just kind of organizing all the information that you have when you're doing this type of problem. Okay, so we have a car that is being towed up a hill. And this is actually an example from Knight, so you can look at the solution in Knight as well. So it's being towed up an incline that's at a 20-degree slope, and it's at a constant velocity, and friction is negligible. So the tow rope can hold a maximum of 6,000 newtons, and the question is, will it break? Okay, so we are going to go through our problem-solving strategy here. Okay, and this is what we're going to use, basically. It's this nice dynamics worksheet, and we're going to look at a sketch kind of what we are looking at, make a coordinate system, make our symbols, right? So let's just redraw that picture. So we have the car going up the incline. Okay, it's getting pulled with tension. Okay, there's no friction. So I'm going to make my coordinate axis along the incline. And I can put the origin right where the car starts. I'm going to say that's my plus x. And this is my plus y. It's going to go perpendicular. Okay. And so what do we know? We know that the incline was at an angle of 20 degrees. So that's one of our knowns. It said friction was negligible, so we have that. Force of friction is 0, which is good because we haven't talked about that yet. And then what else does it tell us? It's going at a constant velocity. So velocity is constant. That means our acceleration is 0. So that's a biggie. And we know the weight of the car, so the force of gravity on the car is 15,000 newtons. And basically what we need to solve for is the tension. Okay, and then we're going to compare that to the max it can hold. Compared to 6,000 newtons. Okay, so it's going at a constant velocity. So here now we think about what all this means, right, in terms of the motion of the object. So, so let's redraw our inclined plane, right? So here's our theta, and we can draw a motion diagram. So it says it's at a constant velocity. So my car is just going to be going equal intervals in equal time. Okay, so that's my motion diagram. And then we're going to go do our free body diagram. So if we look at the forces acting around that, right? So we know that it's got a tension acting on it. It's going to have a normal force from this contact, and it's got the force of gravity. So let's put that in there. So here's my free body diagram. That's my tension. I'm going to turn it this way. My force is normal. I do Fn in the book. It does little n. You can do whichever one you want. And then force of gravity will be down there. Yeah, that's all right. Okay, so that's my x. And that's my y. Okay, and now again, we want to think about that we actually have our fgx there, right? And then over here is fgy. You can draw whichever side you want, but I'm just kind of sketching those in so we know we're going to break that into components. Okay, so we're going to start with Newton's second law. I'd say this is first or second. Basically, the first just means our acceleration is going to be 0. Okay, so the second law says our net force is mass times acceleration. All right, and then we know that this is 0. So in this case, we'll just cross this out. Okay, so net force means that I'm going to sum all the forces. And this is where it gets a little bit tricky. You need to pay careful attention here, right? So if I just look at my forces, and I'm writing these as vectors, which is an important distinction. I'm going to say it's the tension plus the normal force plus the force of gravity, and those all have to add to 0. Now I'm just going to use a little bit of column vector notation here. So what does this mean? The tension means, so column vectors, now I can write the components in their x and y, just break them into their x and y components. My tension is just in the x direction. So it has t in the x direction and 0 in the y direction. The normal is just in the y direction. So it's got 0 in the x and f of the normal in the y direction. And then my force of gravity actually has a negative component, right? So it's got negative fgx, and my y component is down as well too, so that's negative fgy equals 0. Okay, so if we look back at what we need to find, we just need to find the tension. So in this vector equation, so technically, if I wrote this out before I was going to cancel out my acceleration, right, it would be ax and ay. And that mass can just go into that. It's just a constant. So these vector equations are just telling you that you have a separate equation for the x direction and you have a separate equation for the y direction. Okay? The x direction is all we need to solve for tension. And again, we'll just put in here that these are 0, right? We knew that. Okay, so if I pull out my x equation now, I get that tension minus the x component of gravity equals 0, or tension is the x component of gravity. Now we just went through how to derive that. right? There's my theta in here. FGX is FG sine theta. Okay, so tension equals FG sine theta. FG, they told us, was 15,000 newtons, and then times the sine of 20 degrees. And so I find, if we calculate that out, you guys go ahead and do the calculation too. I get the tension is 5130 newtons. Okay, that is less than 6,000 newtons, so the rope does not break. Okay, yay. All right. Okay, so another important concept in this chapter is just the distinction between weight and mass. It's probably something that you've heard about before, but mass is the intrinsic property of something. If I went to the moon or went to Jupiter, my mass would be the same. It's just depends on how many molecules are in my body. Weight is actually the force that's exerted on you by the Earth. It's mostly what we always think about it as. But again, if I was on the moon, my weight would be different, right? There'd be a lower acceleration of gravity, and my weight would be different. Okay. So the acceleration of gravity just comes from the force of gravity. It's one of the fundamental forces of nature. It depends on this constant g, which has a value down here. It's the product of the two masses. So if you were calculating it, let's say between you and the Earth, it'd be the mass of the Earth times the mass of you, divided by the distance between you and the center of the Earth squared. So this distance r is always from the center of one object to the center of the other. So if we were calculating the force between the Earth and the moon, we'd go from the center of the moon to the center of the Earth. The force of gravity, we could say, equals r, is what's creating the acceleration of gravity here. And if we solve for the acceleration, plug in the values of g and the mass of the Earth and the radius of the Earth, we get 9.8 meters per second squared. So the force of gravity between you and the Earth is what is creating this acceleration. And because your mass is on both sides of the equation, right, your mass comes into the force of gravity and into the second law, F equals ma, that mass actually cancels out and everything feels the same acceleration of gravity. Okay. All right. Another important concept for this chapter is the force of friction. So we're going to write the force of friction. This is just discovered empirically, meaning from experiments, that the force of friction is some constant that depends on the material times the normal force. And again, our book uses little n, but sometimes we'll write it as big F sub n. There are different types of friction depending on whether you're moving or not moving. So static is not moving, kinetic is moving, and rolling is two objects rolling against each other or rolling by each other. So, and if you, in your book, they have, a table which gives you sort of common coefficients of friction for static, for kinetic, and for rolling. And if you look at all of these, the static friction, coefficient of static friction is actually larger than kinetic friction. And so we could think about this. You may have some experience with this. This is just looking at what force you would exert basically to get something moving, and then once it's moving, to keep it moving. So you have to push on something, and all of a sudden it starts moving, and it suddenly feels easier to keep it moving. And that's actually true because kinetic friction has a lower value than static friction. So friction is always going to oppose the direction of motion, right? And then you just need to think about whether it's static or kinetic. Okay, so we did one example of a problem where we just calculated found one of the forces on an object, and the acceleration was 0. Sometimes the acceleration is not 0, and then we can actually solve for what the acceleration is and link it back to the kinematic equations that we've seen already. And so this is called dynamics. So in kinematics, we studied motion without thinking about what was causing the motion. Now we're to the point where we can actually analyze the forces on something, figure out what its acceleration is, and then also calculate what its motion would be as a result of those forces. Okay, so we'll finish up with one more example problem. And let's look at this. So we have a car that is 1,500 kilograms being pulled by a tow truck. The tension in the tow rope is 2,500 newtons, and a 200 Newton friction force opposes the motion. So, and then it's going to ask what's the speed. If it starts from rest, what's the speed after 5 seconds? All right, so I'm going to jot down some of those details so you guys can digest that. All right, so we have, given the mass of the car is 1,500 kilograms. We are told the tension in the rope is 2,500 newtons. We're told that the force of friction is 200 newtons, and that we're told our initial velocity is 0, and time is 5 seconds, and we want to find the speed. Let's say at 5 seconds. Okay. So let's look at that. Okay, so we'll use our nice worksheet again for organizing everything. So we want to draw the picture again. My car. Okay. So it's being towed right by a rope. We have some friction acting back on it. I'm going to put my coordinate system here. I'll put it right where the car is starting, so this will be my origin. So here's my plus x, here's my plus y. Okay. We have our knowns here, right? The mass, we have tension, we have the force of friction, initial velocity 0, and then we need to find the speed at 5 seconds. Okay. So we know the tension is greater than the force of friction. All right, so but let's look at our free body diagram first. So we have tension pulling to the right. We have friction's going to oppose that motion, force of friction. We still have force of gravity downward, and we have force of the normal upward. Okay, and let's put in my x and my y coordinates. Okay, and so that means we're going to have an unbalanced force here, right? That's just T, not an F there. So my motion diagram should show an object that's accelerating, right? So my dots will start close and then they'll get bigger, further apart, not bigger, further apart. Okay, so that's my motion diagram. And force ID we kind of did up here, right? Looking at the forces that are acting on it. Okay, so now we're going to start with Newton's second law, and start F net equals mass times acceleration. Okay, so what we want to do, right, is find our acceleration, and then once we have that, we can link that with the final is the initial plus AT. And this is what we're trying to solve for. Okay, so but first we need to solve for our acceleration. So our net force, right, this is the sum of the forces. So again, I'm kind of putting this down here as vectors. I have a tension, I have normal, I have friction. I'm not putting any directions in yet. I'm just putting in the forces. And I have the force of gravity. We'll worry about directions when we break them into their components. And that's mass times acceleration. Okay, so let's now put them into the column vectors, right, where we can just compactly write the x and y components of everything. So tension is in the plus x-axis, so we get a t there and 0 there. So notice I'm not doing the vectors, right? I don't have my hats over that now, or the arrows. Okay, the normal has a component in the y direction and nothing in the x. Okay. Force of friction is in the negative x direction, minus force of friction, and nothing in the y. And the force of gravity, we're on a nice flat surface here. It's got 0 in the x, and everything is in the downward direction in the y. And that equals MAY. So that is max and may. Right, okay. All right, so now if we look at this equation too, right, there is not going to be any acceleration. We're balanced in the y direction, so ay is 0 actually. Turns out we don't actually even need the y equation. But so keep in mind now, once we have things in column vector notation, right, this whole top row is a separate equation, and the whole bottom row is an independent equation. Okay, so if we did for some reason need the bottom row, right, it would just tell us that the force of the normal minus the force of gravity equals 0, or that the normal equals the force of gravity in this case. All right, so that's good. Doesn't really help us with this problem though. Okay, so now let's bring out our x equation. So we have tension minus the force of friction equals max. That's what we want to solve for. So we can divide both sides by mass. And we get the acceleration is tension minus the force of friction divided by the mass. And now I can plug in. My tension is 2,500 newtons. My force of friction is 200 newtons. And my mass is 1,500 kilograms. I did not calculate that. Let's do that quick. So we have 2,500 minus 200 divided by 1,500. I get the acceleration in the x direction is 1.53 meters per second squared. All right. So now we can go to kinematics. Right. This is what we've done before. Okay. So we want to just find its speed. That's actually just going to be the x equation, but just to be consistent here, right? The initial plus at. These do have v final x, v final y equals v initial x, v initial y plus axt and ayt. Of course, everything in this case is 0 in the y direction, so you just end up with the x. V final x is v initial x plus axt. And starts from rest, so that's 0. So v final x is our acceleration, 1.53 meters per second squared times our time, 5 seconds. Let's check that out. 1.53. I'll have to just do up arrow there. Times 5 seconds. 7.67 meters per second. And that's it. Okay. Yep, I'm going to stop there.